So let us now turn the math into code, and I want to show the code first again, and then I want to show how to implement this in our package. So first we want to call all those variables that we need. So the length of the time vector t, then h was the list containing all these state vectors, and c is the equivalent of h, then also o, which is the matrix containing all the values from the output gate, I for the input gate, and so on. And of course, we want to call our activation functions. And then we want to start our actual backpropagation through time. So if we run the reverse process, we go to the last point in time, t, and then we extract dht from the last point in time that we get from the dense layer. And all the columns correspond to the particular state vector ht for this particular time point. So this will be a vector. So that for every time point, we have as many entries as states, which is the number of neurons in our case. So this is a vector. So for every time point, we have a vector, which has the length and neurons. So now we run our forward part just reversively. So we use the command reverse in the loop, and we start with the time point with the last time point. So we have to extract xt. That's what we derived earlier in the math. And then we have to calculate the derivatives with the tangents hyperbolicus. So we have dht. And also here, take a look at dht. So we have the initial value, which comes from the last point in time. But then in the loop, we also have to recalculate dht. And remember, dht is being calculated by two parts. So the first part comes directly from the loss, which we have here. And the other part comes from the previous cell. And I will show this again later than in a few lines. So, but then we just calculate all those derivatives where we have to multiply those values element-wise, so according to the structure of the cell. So we have all these derivatives of ct. And then we also calculate the outer and inner derivatives of all the activation functions. And then at the end, of course, we multiply those outer derivatives with the final inner derivative to get the changes of the different learnables. And we do this for all the different gates. So this is pretty much what we derived in the equations. So, and here's the part of the DHT. So if we do the math, then the DHT from the previous cell comes from all those derivatives, because that's where we have an HT minus 1 in the equations. So this is the information we pass on to the previous cell in time when we do the actual backpropagation through time. But then we also have to add the information from the loss directly from the corresponding time point. And since we calculate DHT for the next step in the loop, we have to take in t minus 1, so not the t, because the t comes from here, that's the current value. But we have to calculate DHT for the next step backwards in time, and therefore we need the value, the d values from that particular time point, which in this loop is t minus 1. And then we have DHT for the next time step. Well, and of course, then we also want to save h, for example. So we have to implement all those lines. And then, of course, in the next chapter, we want to test it. So therefore, let me just go back to our code first. And now we want to implement the backpropagation part in our code. So in order to do so, let me just also first go back to the forward part. So we have all those things that are, all those variables that are defined in the forward part. And now we call the LSTM cell, and we also want to make sure that we keep track of all those states now. So for example, we of course want to keep track of the values that are generated in the different gates. So let me just add those lines here. Because when we run the backpropagation part, it might be, for example, if you just implement all those lines of code, that you might have a typo, something goes wrong. And in order to figure that out, it always makes sense to follow those values that have been generated for the different gates. Also, of course, for the different states, to figure out if there are error messages, what went wrong. So we do this for the different states. So we want to keep record of all those states. And also, we might want to take a look at those values that are generated by the different activation functions. So please go to the part where we have the forward part at the end, where we call the LSTM cell, and then just also add those things here as well. So just in case something goes wrong, and of course you need this definition also if you run it in, so run the forward part over the different epochs. So otherwise the absence of those lines will also create an error message. So let me just save that. And now we want to implement the backward part. So let's now implement the backward method. And we get the D values from the dense layer. So we still don't have the dense layer, and we're going to implement this as well. So we start with the backward part, and maybe you should also take a note and write in your code, okay, the DHT is the inputs from the dense layer. So what I'm going to do now, since this part is a bit more delicate, and it's a very technical part, so I don't write it live. I just rather copy and paste it from a code that works already. But it's, of course, still want to explain you what it does. So of course we want to call all these variables. So don't forget T, H, and C, maybe in this order. It helps to remember it. Then we need all the information from those different gates. And of course we need to multiply those values at some point with CT or some of those values. And we also want to call the different activation functions, where we have calculated all those values for every time point in the forward part, which is, again, this part here, when we call the LSTM cell itself. So now we need those entries. Again, we need it because we have to multiply the outer derivative with the inner derivative of those activation functions. And the inner derivative is generated by using the input in both cases, for the sigmoid and for the tangents hyperbolicus. So they have similar properties. And then we multiply these derivatives with the outer derivatives, with the D values. But the point is that we have these inputs here we need for calculating the inner derivatives, so we need to call all the activation functions. So now let's start with the first value from the last time point. So we get just DHT, which is a vector. So for every state, so for every time point, we have as many states as we implemented in the beginning with self and neurons. So this is a vector. Let's say length 200 or something. And now we start with the actual backpropagation through time. So let me just make some space here. You want to implement everything here. So that's our backward method. I want to show this again. And now we start with the backpropagation through time. So first of all, we extract xt, and we also want to reshape it just to make sure that the np dot operations are going to work. And then remember, the first order derivative is the tangents hyperbolicus, where we use tht as an input, multiply this with the inner derivative, and that creates an output. And we're going to need this output quite a lot. And you see, we need tht for every time step. And the contribution for DHT comes directly from the loss function, or from the loss, which of course went through the dense layer. But it also comes from the adjacent cell, adjacent in time. But for the first step in time, of course, there is no adjacent cell in the future. So we just take this value as an initial value and add it here. But then we have to recalculate DHT at the end of the loop. Maybe let me actually just copy and paste it first, because then you see where it comes from. So of course we don't have all the other derivatives, you know, that's the reason why we get an error message. But that's where we have to calculate DHT, and we have to do this for the next step in time. So we have to calculate this value and plug this into the backward method. And then it has to have the information from the cell, from this current cell, because for the next cell in time, we need to use it for calculating this derivative, but also from the loss directly from this time point. And since we calculate DHT for the next time point backward, then we have to have a t minus 1 here, if this is the current time t. And then we have the correct value DHT for the next point in time where we can calculate the derivative. Okay, so then we have the outermost derivative, and with that we can calculate dct with respect to all these different gates, f, I, and c tilde, which gives us those derivatives here. So we use np multiply, because in the forward part, they are also being multiplied element-wise. Be careful, there has to be a t minus 1 here. And then we add all the derivatives of the activation functions. So all the derivatives of the activation function. So therefore, we have all the outer derivatives, and now we can start with the calculating the derivatives of all the learnables. So when you do that, make sure that you assign those values correctly to those variable names, so that you do not confuse, like say the outer derivative of the sigmoid of the forget gate with a learnable from, let's say, the output gate. So please make sure, like in my case, there's always an F where it belongs to be, and then you do the exact same thing for all the other gates. So you do this for the input gate. And you see that's lots of code. And that's the most delicate part if you implement this. Because even though if you have done the math correctly and you know what you're doing, You can still have typos, especially in this part here. There's also t-1, which comes from the equations that arise from the particular structure of our cell. So we do this for the input gate. We also do the same thing for the output gate. And finally, we do that for those variables that have the subscript G. And then we are complete with the backpropagation part. So let me just scroll through the backpropagation part once more. We also probably still want to keep track of age. So even though we just call age here, maybe we should still save age. So maybe we should just say fill age equals age. So let me just scroll through the backward part again so that you can compare your code to mine. So we just call all these variables because we're going to need age and C for the different time steps. Of course, we also call our activation functions, make sure that they have the right assignment. Then we start with the initial value of backpropagation through time, which comes from the loss through the dense layer. And then we start with the actual backpropagation part, where we calculate the outermost derivatives. First of all, tangent hyperbolic is true, and then CT, so dCT dFt, dCT dit, dCT dC tilde t. And then we calculate the derivatives of the different activation functions. And then we can calculate the changes of all the learnables. All right, so then we hope that there's no typo, and then we're actually ready for testing our backpropagation and to test the full backpropagation. And therefore, we're going to use our script where we test run our LSTM. And before we modify our optimizer and use the optimizer, we just want to make sure that our backpropagation works at all. And that's subject to the next chapter then.